types of matrices. The simplest matrix is an identity matrix, right? Then the next simplest matrices what we have are diagonal matrices. So diagonal matrices are something like I have D1, 0, 0, 0, 0, D3. Only there are elements around the diagonal, half diagonal elements are 0. If you have two matrices that are diagonal, then they commute. AB is same as BA. And if you have a matrix A, you can define A inverse as 1 over D1, 0, 0, 0, 1 over D2, 0, 0, 0, 1 over D3. Because when you multiply A inverse, you should get identity matrix. So the diagonal elements are reciprocal of the same. Not only that, you have a very good advantage that if you have some function of A, f is some function of A, then if A is diagonal matrix, this is exactly f of D1, 0, 0, 0, f of D2, 0, 0, 0, f of D3. Whatever is the function, suppose if it is exponential of A, it is exponential of D1, exponential of D2, exponential of D3. So if you have diagonal matrices, you want to write in terms of functions of a matrix, it's very convenient.
Is that critical theorem, sir?
Huh?
This last one is the critical theorem.
The last one is, yeah, you can prove it. Prove that. Essentially, the proof is assuming that if you have a function f of a, suppose if you have a function f of x, this can be written as f at 0 plus df by dx, evaluated at x is equal to 0, x plus d2f by dx2, dx2 evaluated at x is equal to 0, a squared by factor x squared by factorial 2, and so on. Such an expansion can be done f of a. Whatever is the coefficient here for that function, you will put it there. Okay, for example, if you have exponential of a is nothing but identity matrix plus a squared by factorial 2, and so on. So you can write down this one like this. But if it is a diagonal matrix, then what happens is a square is nothing but d1 square, d2 square, etc. So you will see that this will be like 1 plus d1 square by factorial 2, 0, 0, 0 here, 1 plus d2 square by factorial 2, etc. 0, 0, 0, 1 plus d3 square by factorial 2, 0, 0. So this becomes e power d1, e power d2, e power d3. So this is a kind of proof that any function of A can always be written as a function of.
This comes in quantum mechanics, this exponential type of.
Yes, it comes in quantum mechanics because in quantum mechanics, if you consider evolution is always e to the power h times t. Now, if you have a finite dimensional vector space, if you have an evolution of spin systems, for example, what comes in the exponential will be a 2 by 2 matrix or a 3 by 3 matrix. So, exponential of the matrix is required. It can be even in rigid body dynamics. When we have classical mechanics, when we talk about rigid write down rotations as when you write rotation in terms of the generators, you'll always write e to the power some matrix into some angle. So exponentiation of the matrix it comes in classical mechanics also. And of course, the determinant of A is equal to V1, V2, V3. This product of the diagonal elements. The determinant of A is equal to V1, V2, V3. Okay? Actually, this reminds me that I must ask a question here, and I should give it as a homework today, so that you can practice. We discussed about the vector space V. Okay, so this is homework. So we discussed about vector space V, which is a set of all two-dimensional matrices. Set up our two-dimensional matrices over a complex V, and we said this is a vector space, it's a four-dimensional vector space. Okay, so I want to define the inner product. I want to define distance between two matrices. Possible to define an inner product and a norm for each vector. Suppose I have a two-bit matrix, another two-bit matrix. What is the distance between these two matrices? Such questions are. Because since we define it as a vector space, we can also define an inner product. So what kind of inner product will we define for this vector space? I want to have a scalar. Take two vectors, I want to have a scalar. That means I want to have two matrices, but the scalar should satisfy the properties that listed under inner product. And it should induce a norm. That means when I take the same matrix and then I use that definition of inner product, I should get a real positive number. So what kind of inner product do we define for this? Okay, so I suddenly remembered this. We omitted discussing about this. It's good, so we can think about it. Okay, so this is the first type of matrices that we simplest.
Can you briefly say something about diagonalization? The need for diagonalization?
Yeah, I will come to that. That's probably tomorrow I will discuss about diagonalization procedure and need for diagonalization, which matrix can be diagonalized, which matrix cannot be diagonalized. See, that's not only required in quantum mechanics, it's also required in classical mechanics. For example, if you remember what you did in rigid body dynamics, you consider some object and write down, you have some coordinate system with respect to which you find out the moment of inertia tensor of a rigid body, and then you look at a coordinate system in which the moment of inertia tensor is diagonal. That becomes what is called a body set of axes. You have any arbitrary space set of axes with respect to which moment of inertia tensor will have all elements. But if you go to a body set of axes, then it will have only diagonal elements. So diagonalizing moment of inertia is actually finding the body set of axes. So that is done in classical mechanics. So the next simplest type of matrices that we have are called tri-diagonal matrices. So tridiagonal matrices, okay, sorry, I think tridiagonal matrices are not really important. Talk about triangular matrices. Tridiagonal matrices are important with numerical analysis, but anyway they are not very triangular matrices. Triangular matrices, there are two types. One is called lower triangular matrix. That means you will have some kind of a L11, 0, 0, L12, L22, 0, L13, L, I should write it as 0, 2, and 31, 32, and I'm writing 3 by 3 is, you can define this in by matrices. So all the elements above the diagonal are zeros. This is lower triangular matrix. You can also talk about an upper triangular matrix. Upper triangular matrix, I call this as L, upper triangular matrix, writes as U11, U12, U13, 0, U22, U23, 0, 0, 22. That means below the diagonal all elements are 0. So this is like a upper triangle, this is like a lower triangle. That's why this name, upper triangle matrix or lower triangle. This is also very useful to define. You can actually, you can transfer. I do not know if people are familiar with some numerical methods. If you have some equation like this, Ax is equal to B. If you want to do this x on a computer, you know B, you know A. If you want to get x on a computer, you do something called LU decomposition. You can always decompose any square matrix as a product of lower triangle and upper triangle matrices. So in a computer algorithm, it is very easy. What is guaranteed for me is that A can be written as LU. So that means LU into X is equal to B. Okay. So I can say that Ux is an unknown quantity. I can call it. Okay. So L into some unknown quantity G is equal to B. This is known and this is known. So I can find out G first. And then I call Ux is equal to G. G is known now because I solved this already. And hence I can find out X. This is called LU decomposition. By finding A as a product of lower triangular and upper triangular, I can solve this problem once by backward substitution and as by forward substitution I can do it. So of course I don't want to go into details of LU decomposition at this moment, but this is an application. In this case also you can see that the determinant of L is product of L11, L22, L22. Similarly, determinant of U is equal to product of U11, U22, U22. In fact, this is very, very important. See, if you want to write an algorithm to calculate determinant of a matrix on a computer, okay, and if you expand your determinant in terms of writing A11, A22, A23 minus A11, A23, A23, A32 like this, you will have to write, if you have an n by n matrix, you have to write n factorial terms, correct? And each term will have n minus 1 products. So if you calculate the number of floating point operations that your computer has to do in calculating a usual expansion of the determinant, for something like 100 by 100 matrix, the computational time required will be on the order of age of the universe. So you will never be able to complete finding the determinant of the matrix on a computer. So you essentially what you do is you reduce the matrix by an appropriate transformation to the lower triangle or upper triangle, and then the determinant is simply product of the diagonal elements. So you can handle any matrix size using this kind of thing. So triangular matrices are very useful, especially when you are doing computation, writing algorithms.